This video describes an easy process for constructing air bearing pads using minimal machining. The primary objective of this project is to make manufacturing very simple while still producing well-functioning bearings suitable for use in applications such as linear axes. The described process can easily be adopted to different bearing sizes. Before we begin, let's quickly recap how air bearings work. Feel free to skip any segment of the video you are not interested in. Imagine the air bearing as an upside-down cup placed on a flat surface. An air inlet with a restrictor nozzle allows a small amount of air to flow into the main chamber. When the pad is well above the surface, the small amount of air that enters the chamber can quickly escape through the bearing gap on the edges. Therefore, almost no pressure is built up within the chamber, and only a very small amount of force pushes the bearing upwards. Contrarily, if the pad sits directly on the base surface and completely seals the cup, the pressure inside the chamber will rise until it reaches the feed pressure. This high air pressure will exert a large upward force on the bearing. So, the smaller the gap, the larger the force pushing the bearing upwards. Now when the air bearing is loaded with a force within its working range, the gap height will adjust until an equilibrium is reached, and the air produces an upwards force equal to the load. Since all the air within the chamber can be compressed, and thus acts like a large spring, it makes sense to reduce its volume as much as possible by filling the chamber with solid material. As shown, only a small gap between the surfaces remains, which in real bearings is roughly about 10 micrometer in height, a fifth of a human hair. Such a small gap will reduce the air volume, as desired, but will also impede the airflow under the pad, leading to pressure loss towards the edges and hence a lower lifting force. We will counteract this problem by adding small channels to the bearing surface that transport the air towards the edges of the pad and restore the pressure in the outer regions. Here you can see a simulation of the pressure distribution for a rectangular pad. On the left, no channels are present, and the pressure falls off quickly. On the right, channels provide a low resistance path towards the edges and keep the pressure high in the middle region, increasing the lift and force. Note that a major fabrication challenge is to make the pad sufficiently flat. Since the bearing gap is only a few micrometers in height, even small deviations from the ideal shape will either cause pressure loss or collisions with the base surface. In this picture, you can see all the tools and materials needed to build the air bearing pads. A metal disc is used as the main body of the pad and serves as the mechanical support for the bearing surface. In principle, you can use any type and size of metal disc, but if you do not have the tools to cut these from bar stock yourself, it is easy to buy them online. For example, the one in the image is a stainless steel end cap used for railing pipes. Next, we have a small 2mm brass pipe that will be used to connect a hose to the bearing pad. As for the consumables, regular plaster will provide a porous material for the constrictor nozzle. The bearing surface itself will be molded from JB Weld. I highly recommend using this brand of epoxy, as it has excellent adhesion properties and forms a really hard surface. Additionally, it is a steel-filled epoxy, which makes it more dimensionally stable. Finally, a wax-based mold release agent is required to prevent the epoxy from sticking to the mold surface. Here, semi-per monofilm is used, which forms a nice, thin, and smooth anti-stick layer. In the tools category, we need a good quality piece of float glass. A float glass mirror can also be used, but be aware that the planarity of cheap products might not be as good, which can degrade the performance of the pads. Furthermore, a 2mm metal drill and a drill press are required, as well as a needle, or preferably a scribe. Last but not least, we have 3 simple 3D printed tools that need to be adjusted to fit the dimensions of the metal disc. It's best to take a look at them in CAD. The first part is a fixture for the metal disc that aids in drilling the nozzle and the feed line holes at the correct positions and angles. The protrusions on the top allow for easy alignment with a vise. All the 3D printed parts are parametric, so they can be easily adjusted to the desired pad size in Fusion 360. For this part, the correct diameter and height of the metal disc have to be entered. The second part is used during the molding process to keep the metal disc at a precise distance from the glass surface. 3 screws are used for height adjustment. Again, the model is parametric, so it can be easily changed to fit the diameter of the metal disc. The last 3D printed part works like a mini lathe and will produce the outer circular channel by scoring the bearing surface at a fixed distance from its border. The part itself resembles a plate with a couple of holes. 3 of them are used to tightly constrain the metal disc with 2 screws and an adjustable clamp. The 4th hole holds the scoring tool, which can either be the tip of a scribe or, better yet, an off-the-shelf engraving tool bit. The tool bit is adjusted to slightly protrude the surface and is fixed in place with another screw. Again, this model can be adjusted via a few parameters to fit the dimensions of the available materials. The distance of the circular air distribution channel from the border can also be configured here. The design of the new pad is very similar to this old rectangular design made from glass. It was briefly shown in a previous video and has a porous restrictor nozzle as well as a channel at a fixed distance to the border. 2 feed channels intersect in the middle, delivering air from the center to the outer region. Although the pad worked well, the glass material was challenging to machine and special tools like diamond whetstones and glass drill bits were required. The new pad is made from metal, which is much easier to work with. The round shape also has benefits. First, the pad rotation does not need to be constrained by the mounting system. Second, a small pad is more tolerant of planarity deviations in the bearing surface than a large one, and for a given pad area, a round shape has the minimal size. The epoxy bearing surface is also easier and more consistently scored compared to glass, and it does not suffer from chipping. Overall, the new design aims to improve ease of manufacturing, compactness, and performance. This chapter shows the molding process of the bearing surface and the necessary preparation steps. The preparation starts by drilling the feed holes into the metal disc using the 3D printed fixture. Please make sure that the holes intersect as shown in the image on the top. Next, the 3D printed molding rig is adjusted. It fixes the metal disc at a small and precise distance above the molding surface. 2 layers of office paper with a total thickness of about 100 micrometer are used to set the correct spacing. The screws are turned until they just touch the surface. When done, add an extra quarter turn to create some additional space. Place the 2 layers of paper and the prepared jig onto a flat surface. Make sure that the screws rest on the surface and not on the paper. You can check for proper spacing by turning the jig and checking that the metal disc stays stationary. If everything looks good, use super glue to fix the jig to the pad using the spacing defined by the 2 layers of paper. Note that the super glue might need longer than usual curing times of about 30 minutes due to the large gap size. You may use accelerators or a different kind of glue to speed up the process. The actual molding process starts by coating the float glass surface with a suitable release agent. The goal is to have a thin and smooth surface coating. For the product I am using, the surface is first covered by the liquid, followed by a short venting time to let the solvents evaporate. Afterwards, a paper towel was used to polishing away any excess. I advise to follow the instruction for the product you're using, but the usage is probably quite similar. Next, the epoxy resin is dispensed and thoroughly mixed. The resin is then spread onto the surface of the metal disc. Try to avoid any air bubbles and make sure the layer thickness is above 1 mm to have sufficient excess material for the molding process. Now take the molding jig with the metal disc and place it onto the prepared glass surface. To prevent air from being trapped, angle the fixture when lowering it down. Then gently push and wiggle it further down until all 3 screws touch the glass surface, giving you a precise and even film thickness. Excess resin will be pushed out the sides. You may check for voids and defects, which may form if not enough resin was applied in the previous step. Once the epoxy has cured, remove the molding jig. Next, insert a small screwdriver into the feed hole and carefully pry off the pad with a twisting motion using a larger flathead screwdriver. Demolding can require some force, especially for larger pads, so avoid placing the pads too close to the edge of the glass plate. Excess material should be trimmed away. Pressing the pad against a surface while trimming helps prevent the edges from breaking out. Using a prism as an optical flat, we can check the planarity using thin film interference. The goal is to have even parallel fringes. In this particular case, I would estimate the distance to the reference surface to be below 150 nanometers. In the next step, small channels for air distribution are created. A circular channel is formed first using the 3D printed tool presented earlier. The tool is adjusted to hold the pad securely while still allowing it to rotate. The height of the scoring tool is adjusted by tightening the holding screw slightly and then pressing the tool down with a piece of aluminum. This embeds the tip slightly into the surface, producing the desired protrusion. You can verify the height by scoring the aluminum and inspecting the channel created. The goal is to achieve a depth of approximately 100 micrometer. Once everything is adjusted, place the pad into the tool and rotate it while pressing down until you feel that no more material is being removed. Using the drill jig from earlier, the center is carefully marked with a small drill bit. With the center marked, the two cross channels can be formed manually using a ruler and a scribe. Take care to create even channels that do not intersect with the circular channel from the previous step. With a piece of checkered paper, you can visually align the second channel to be perpendicular to the first one. The final step in the build process is creating the restrictor nozzle through which air is fed to the underside of the pad. The drill jig is used to drill out the epoxy resin from the center hole. The pad is then placed onto a clean glass surface, and the center hole is filled with plaster to form the restrictor. The plaster should be mixed fairly thin to increase porosity when cured. You can adjust the porosity based on your application and feed air pressure, but I have found a 1-to-1 ratio of plaster to water works well. After a few minutes, the plaster thickens and reaches the right consistency for filling the pads. A small stick is used to agitate the plaster and remove potential air bubbles. The feed nozzle is completed by sealing the top with a small ball bearing and super glue. The bearing also serves as the mechanical interface for the bearing pad. After drilling out the plaster from the feed hole on the side, a small piece of brass tubing is glued in place to which a hose can be connected.